And I want to talk today about Chimera chains, which apply heterogeneous trust protocols for cross-domain atomic transactions. We don't have a formal paper on this yet, but if you want to read more, we do have a blog post here. I am technical lead for Typhon, which is a state machine replication stack built by Alex, Tobias, Nakeeb, TG, and myself in no particular order. Heliax is building Typhon as part of the ANOMA fabric of blockchain protocols. Right now, ANOMA-based prototypes use Comet BFT, formerly known as Tendermint, which is pretty common in like the Cosmos ecosystem. But Comet/Tendermint isn't perfect, and we think that we can do better. So we're building Typhon to replace Comet. It's going to improve some throughput and latency, but one feature that has a huge impact on our design is that it's going to enable a new kind of sidechain, a protocol that we call Chimera chains, which support multi-chain atomic commits. And it's these Chimera chains that I want to dive into today. So before I get into that, I want to say a little bit about the assumptions that we're building under. Like the Cosmos ecosystem, Typhon is built assuming heterogeneous trust. Different state machines, different blockchains have different trust models with overlapping quorums and validators and whatnot. But while most, for example, Cosmos software, including Comet, is kind of oblivious to heterogeneous trust, Typhon is not. Hopefully this lets us do a number of things more easily, even something as simple as running multiple chains on the same validator. Validators running multiple Typhon-based chains will be aware of cross-chain opportunities, and the same software can be used to add or even start up new chains on demand, which will come up later. We don't necessarily need to make, for example, separate redundant peer-to-peer connections between the same pair of validators for two separate chains or state machines. Next, I want to talk about what we're trying to build at a very general level. So the idea behind most blockchains is to maintain a replicated state machine, something that's been studied for decades. This machine, which is replicated across all the validators, starts at some initial state, and each state transition updates it to a new state. Usually, individual pieces of state have well-defined permissions on who is allowed to update when, such as only Alice is allowed to deduct things from Alice's account. These checks are validity predicates or smart contracts or stuff like that. We're going to leave that pretty abstract for our purposes. Usually, we want our blockchains to be highly available. This means that they should be easy to read, at least if you have permission to do so. But it also means that everyone should be able to commit transactions without censorship and without slowdown. So we want high throughput. The really tricky part, however, is that we also want high integrity. We want everyone to agree on the replicated state machine, even in the presence of failures. And in the case where we're talking about, we care about chains that have finality, where once we've decided that a transaction happens, that a state transition has taken place, all replicas eventually respect that. So decisions are final. So Comet is intended to do all of these things. It provides a basis for maintaining a replicated state machine with relatively high availability, relatively high integrity, depending on who your validators are, of course. And Typhon, as I said, is intended to improve on Comet. So we're hoping to support a pretty generic language of state machines, and we hope to improve on Comet in some of these areas. So if you're interested in a new engine to run your state machine on, or if you think your state machine has interesting requirements, Typhon would love to hear from you. So one big improvement that we want to make for Typhon is to handle atomic transactions that update state on multiple chains. This requires changing some of the definition of what it means to agree on the state machine, since different chains have different validators, different trust models. Typhon will enable a new technique, which we call Chimera chains, that will hopefully make these cross-chain transactions easier in some of the most important cases. So Chimera chains exist to address this cross-chain atomic commit problem. So I want to get into explaining what that problem looks like. We hope that in the ANOMA ecosystem, there will be many active chains with different sets of validators with different trust models. And we can use and even extend some existing tools like IBC to securely send messages from one chain to another. And Comet can handle this kind of thing perfectly well. But this kind of asynchronous communication doesn't solve a specific difficulty of multi-blockchain applications. For concreteness, let's consider the train and hotel example. So suppose a hotel tracks rooms on red blockchain and a train tracks seats on blue blockchain. And now I want to buy a train ticket to Paris if and only if I can also buy a hotel room for Paris, something that has been a problem for me in the past. I don't want to buy one and then find out that the other one is sold out. One traditional way to do this would be with a multi-phase commit. So starting with some state, each chain would commit a transaction saying that it wants to do this multi-phase, multi-chain transaction, and it's locking the relevant state until all the relevant chains are committed. No one is allowed to change this state until it is unlocked. So here we're putting a lock on this train seat. I haven't booked it yet. In principle, this could still be aborted, but no one else can buy it while it's locked. The state stays locked even as more transactions are processed until all the relevant chains have locked all of the relevant state. And now I've also locked a hotel room. It's not booked yet, but no one else can book it. And then the chains need to receive messages from all of each other, indicating that each of the other chains have indeed locked the relevant state, committed to the multi-chain transaction. And at last, that transaction can take place. The state can be updated and unlocked. So finally here, I have actually booked the hotel room and the train seat. And fundamentally, multi-phase commits like this have at least three problems. So the first is liveness. If blue chain locks its state and then red chain dies, then blue chain state stays locked. Despite the fact that conceptually, blue state machine is supposed to be live, all of blue's validators are running perfectly well. Resources on blue chain have been made unlive because of failures outside of blue chain. So in this example, the train ticket stays locked and unbookable because of failures in the validators that the hotel trusts, which have nothing to do with the validators that the train is supposed to trust. Secondly, and more simply, it takes at least two rounds. Every multi-chain transaction requires at least 2 blocks worth of latency, complete with the necessary commits and proofs that you need to send a message reliably from one chain to another. And finally, whichever chain commits last gets to decide effectively when this transaction happens. And in a market of fluctuating prices and opportunities, that can be valuable. We don't really want to incentivize chains to delay anything. We usually want to minimize latency in these kinds of things. But conceptually, these chains already have atomic mechanisms for committing their own blocks. What they're really modeling here is just trying to take 2 portions of their chains and commit them atomically to both data structures, like it's one big atomic block. We described how to do this, or at least one way to do it, in 2020 at Opus with Heterogeneous Paxos. So in principle, we could use something like Stellar here too. We're going with Heterogeneous Paxos in this design because it's designed with a closed system model where we know everyone's safety and liveness requirements in advance, something that most chains define, for instance, in terms of stakeholders. So to understand at a high level what Heterogeneous Paxos can do, we have to talk about quorums. Here, we're talking about chains with finality. So that means in an asynchronous or even in a partially synchronous system, there must be some set of acceptors, validators if you like, but we're going to call them acceptors, called quorums, that a learner can hear from, or a user can hear from, or a replica can hear from, and they can say, I have heard enough, and I know that this block is committed. So suppose that for red chains replicas, these quorums look like this. Crucially, the quorums all intersect. If you ever have 2 quorums that don't intersect, then it's possible for one person to hear from one quorum and another person to hear from another quorum, and they could all operate completely separately, and there's no way to be sure they agree. What's more, there needs to be a safe acceptor in that intersection. If they were all unsafe, if they were all Byzantine, then they could act one way for the purposes of one quorum and another way for the purposes of another quorum, and we'd be just as screwed. So back to our example, let's assume that blue similarly has 3 quorums that all intersect. And things get really interesting if each of the red quorums intersects each of the blue quorums. This is the situation where we can, as long as each of those red-blue intersections have a safe acceptor, do heterogeneous Paxos just fine. We can commit a block, and as far as blue is concerned, using only a blue quorum, and commit a block as far as red is concerned using only a red quorum. And the red and blue quorums will agree whenever that intersection has a safe acceptor. So we get a heterogeneous Paxos with a well-defined atomicity guarantee when red and blue will agree. And I'll get a little bit into that more later. The interesting thing here is that there's actually a huge amount of overlap between the validators of different, mostly proof-of-stake blockchains. I know you can't read this giant grid, but it's really quite common for half to 2/3 of the validators of proof-of-stake chains to be shared, in part because there are a small number of professional validator companies that run proof-of-stake validators. But this intersection requirement opens up a fundamental question. Suppose that all the red quorums intersect the blue quorums. This means that we can have a heterogeneous Paxos for red and blue. And all the blue quorums intersect the quorums from green chain. And this means that we can have a heterogeneous Paxos for blue and green. But not all red quorums intersect green quorums. This means that we can try to do both of those heterogeneous Paxoses, but bad things can happen. So for example, suppose this red quorum decides on this shared block. And red can even build on that block, moving on with its life. And suppose that this green quorum decides to append this shared block. And then green chain moves on, appending more things. Note that red and green quorums don't intersect. There's no way to guarantee that they will hear from each other before making these decisions at all. If we inserted that requirement, we'd be requiring that the green state machine replicas have to wait for red acceptors, which is not something that is in their trust model. So now blue is stuck. Blue quorums can't decide on either of those blocks. To decide on either would be to break the fundamental guarantee that they'll agree with green on shared blocks and they'll agree with red on shared blocks. They can't do both. And we call our answer to this challenge Chimera chains. So Chimera chains are new additional blockchains, a separate place where cross-state machine atomic transactions are scheduled. And we can have a different Chimera chain for each possible heterogeneous consensus. Okay, so most blockchains are designed for high throughput, so running them is actually quite resource intense, but these Chimera chains are really only intended for multi-chain atomic commits. So for some chains, these are going to be quite rare, and that means that we want to keep these lightweight. We only start a chain or commit a block on demand. So I'll get into how one might program the Chimera state machine in a minute, but I wanted to point out that it's crucial that we have communication between these Chimera chains and their base chains. In fact, since they're running on the same quorums of validators, the same replicas, that communication can be, in a sense, synchronous. A transaction on a Chimera chain can read state that was written to a base chain, a constant number of rounds of consensus. For technical reasons, 2 is very convenient prior. Likewise, a base chain can read state written on a Chimera chain, a constant number of rounds of consensus prior. I'm just going to zoom in on one of these Chimera chains for a moment. So mostly to check out what happens to a Chimera chain when that atomicity guarantee isn't met. So to kind of define what atomicity means, we have to look at what happens when you don't have atomicity. So suppose that this blue quorum has decided, for the sake of simplicity, all of these blue and Chimera blocks. And replicas for blue chain believe that these blue and Chimera blocks dictate the state of the blue and Chimera state machines. And now let's consider some red replicas. For the sake of simplicity, let's suppose that this red quorum happens to be the one deciding everything of interest right now. And in this intersection, these purple acceptors, this tiny triangle here, they're all Byzantine. They can bisimulate, and red replicas could decide on different Chimera blocks than blue replicas. This is the limit of our atomicity guarantee. Replicas only agree if their quorums have a safe acceptor in the intersection with each of the other one's quorums, and that didn't happen here. However, even if we lose atomicity, that doesn't mean that red replicas lose liveness or integrity. Looking at things from the perspective of red replicas, all the red quorums intersect all the other red quorums on safe acceptors. And they have quorums that are live, that are untainted by failed replicas, or by failed acceptors. So for the red replicas and their view of the red base chain and the red Chimera chain, there is no fork. There is no inconsistency. There is a canonical set of transactions committed. And the same is true for blue replicas. All blue replicas quorums intersect with other blue replicas quorums on safe acceptors. They have live quorums, so they don't have a problem. All the blue base chain and blue view of the Chimera chain remain just fine. What we've lost is the agreement between red and blue chains, the guarantee that when red and blue transactions are in a Chimera block, either all of them or none of them will be committed. So we can quantify exactly what we get from this atomicity. The two state machines agree when their quorums pairwise intersect on a safe acceptor, and the atomicity guarantee is simply that the chains the replicas agree on will be the same. And so long as those intersections remain safe, we can offer these cross-chain atomic transactions. So even in this works even in an arbitrarily large universe of chains without any global agreement on what our integrity assumptions are and without any particular global ordering. Okay, so how does one actually program a state machine with a Chimera chain? Well, first, let's look at the part that actually runs on the Chimera chain itself. We want a state machine that runs these multi-chain transactions. So recall that the goal of each chain is to support a replicated state machine, an abstraction built on top of some API above the transaction ordering and storage layer. So the easiest way to do this would be within the Chimera state machine to run instances of each of the constituent state machines. Like we said, we want to leave these very broad as to the kind of state machines we can support. So we're trying to say as little as possible about what your cross-chain atomic transactions might look like. We know that we can communicate with these sub-instances via the same API, just like they were running on top of their own chains. Now, the transactions of our Chimera state machine will be bundles of transactions spanning each of the constituent state machines. And so far, we can keep everything within the same API barriers. If our chain schedules an atomic bundle transaction, then our Chimera chain schedules the transactions from the bundle on each of the constituent state machines. Now, the transactions of our Chimera chain, so far, this is pretty much what a shared sequencer does. If you're familiar with like espresso systems, shared sequencers or shared validity sequencing. But a lot of these transactions will want to include computation based on the current state on the other state machine. We want to add some additional communication interface whereby the transactions running on the constituent sub-state machines in the Chimera chain can send information to each other. They can even get replies. They can have arbitrary rounds of communication within the same bundle. This means that we're adding yet another communication interface, this time taking place entirely within the Chimera machine. It's not going to be anything that's literally over the wire, but it's going to require some support from the constituent state machines and their transaction languages, some kind of equivalent of a syscall to send a message to the other sub-state machines within the bundle. By the way, shared sequencers should be able to do this kind of intra-bundle communication as well. So this language design is actually a place where we're looking for collaboration. How do we support the broadest possible cross-chain transactions, while placing the fewest requirements on what each constituent state machine has to support? It might look something very basic like IP, or something slightly higher level like TCP, or even higher level like IBC. I'm not sure what the best place to draw support is. So I want to zoom out a little bit and include the state machines running on the base chains as well, and what programming looks like with those. So we've been looking at the Chimera state machine, the part that is actually on the Chimera chain itself, but most of the time we actually want to think of all of the state under the control of red state machines' trust assumptions like it's one big state machine, and all the state under the control of blue state machines' trust assumptions like it's one big blue state machine. And we're going to do that by having explicit partitions in the state of each of these machines. There's one base partition and then a partition for each Chimera chain. Within each partition, we're going to have some state, and that state is going to have updates that will be serializable, which is to say they're equivalent to applying some transaction to get a new state and then another, and so on in some serial order. And the Chimera partition will likewise have its own state with serializable updates, and the partitions on blue machine will likewise have their own states with serializable updates. But what makes these more like partitions rather than just independent state machines running next to each other in a giant blue rectangle is that these these transactions can read not only from the current state of their own partition, but from recent state, like I said, within some constant number of rounds of consensus, from other partitions within the same state machine as well. Okay, so thus far we've got a bunch of partitions, but what makes the Chimera partitions special is that their transactions are part of those atomic bundles we talked about a minute ago with intra-bundle communication. These Chimera partition transactions are scheduled by the Chimera chain using heterogeneous Paxos. Nevertheless, recall that these partitions remain safe and live under the same conditions as their base chains. So in general, to program on this setup, machines should support transactions that transfer control of portions of state resources, for lack of a better word, from one partition to another. So a transaction on the other partition would read that transfer and can act on that resource. So in some ways, this model is a lot like having exclusive locks on resources. A resource can be held by one partition at a time, and the holder can surrender that lock and give it to another partition at any time. So for example, if you transferred control of your hotel room into your Chimera partition, even if the other base chains in the Chimera chain were dead, you could still run another transaction to transfer control of the hotel room back. It would not be stuck. So that's our programming model for Chimera chains. So I just wanted to take a few minutes to talk about some future work possibilities. There's a whole bunch of performance optimization stuff, but here I want to talk about generalizing Chimera chains. So far we've been steadfastly refusing to change the quorums that the base chains use. The state of the Chimera chain retains exactly the same liveness and safety that it has on the base partition. And then the atomicity guarantees we get for the Chimera chains the result of overlap in existing quorums. But we could use different quorums. We could, for example, use bigger quorums to get stronger atomicity guarantees at the expense of liveness. In the extreme, we could make a Chimera chain where the quorums contain a full quorum from each base chain. So we'd get atomicity as long as any of the base chains remains safe. We'd also lose liveness if any of the base chains get stuck. Of course, we need to be very careful to make it clear to programmers exactly what guarantees they're gaining and giving up when they move state between partitions. And that means that resources probably need permissions on them about what guarantees their resources can be moved into. Another thing we'd like to work on involves finding alternatives to the underlying consensus. I mentioned that Stellar should work just fine for this, but I'd actually like to do some research on a fully asynchronous consensus like Tusk or Honey Badger, which generally rely on shared randomness. So far, we haven't completely sorted out how to do heterogeneous trust in a heterogeneous trust-based randomness beacon, although there is some promising recent research. Hopefully that gives you a taste of the Chimera chain project. They are a general way to atomically commit transactions across multiple instances without multiple rounds or locking resources. We've talked about why they're set up this way and what kind of guarantees they can provide and how one might program state machines with Chimera chains. Chimera chains are intended to, as Andrew Myers would say, make the easy things easy, to allow cross-domain transactions in chains that are already quite similar, that have high overlap, and that should make cross-domain transactions as fast and easy to implement as possible. So we hope that with better multi-chain transaction support, people won't be so incentivized to force all their applications onto a single giant chain. Having many interoperable instances will help reduce congestion and costs, but it also allows each application to choose a trust model that's right for them. Any questions?
We have time for questions. Yes.
How do you guarantee this overlap across different chains? I think you mentioned that they're the same validators who are going to run it, and that is why there's going to be some overlap, but it's not guaranteeing. So is it guaranteeing versus just, hey, that's just out there?
Right. So what we want to do is, just a moment, look at our existing base chains, which already define the set of quorums that they make. And when there is a sufficient amount of overlap between them, then we can launch a Chimera chain. So booting up the Chimera chain is predicated on meeting the basic validity requirement for their trust models. If your trust models don't overlap enough, then you can't have a Chimera chain.
So that would mean some kind of extra infrastructure where they tell each other what chains they're validating.
Correct. The boot up process for a Chimera chain involves some asynchronous cross-chain communication where they talk about their trust models to each other and then agree on what the Chimera chain genesis block looks like.
Good, thank you. My question was here, your pictures always show the Chimera chains composed of 2 colors. So like 2 out of n.
Yeah.
Are you considering also arbitrary subsets, or is this?
Yes, you can do arbitrary sets. It has the same requirement that all of their quorums have to intersect all their other quorums. I'm trying to see if I have a drawing of 3-way Chimera chain quorums, but I think they might be missing. The drawing gets really messy.
Well, after 4 dimensions, it gets a bit tricky
Yeah.
anyway for me.
But you definitely can do n-way Chimera chains as long as they meet that quorum intersection requirement.
Thank you.
Well, I guess my question was similar to yours, Christian, but I was wondering if there's a designated chain to do to manage configurations, basically. But you said it's there's an asynchronous protocol instead to.
There's not a designated chain for managing that. So instead, we are working on an asynchronous protocol for chains to share their trust models with each other so that they can work out if they have enough overlap and decide on what the, I say decide, but technically it's not consensus, on what the genesis block for the Chimera chain has to look like. And then updates to their quorum sets have to also percolate to their view of the Chimera chain, which then ceases to exist if their trust models have changed sufficiently that they no longer meet the intersection requirement.
So it's that's interesting that you can do this asynchronously. I guess a bit surprising.
Well, in this case, what you really have to do is learn what the trust model is for each of the chains, which each of them can volunteer independently, and then the basically genesis of the Chimera chain is derived from there. If one of them has lied, then you can technically form the Chimera chain. It just will be very boring because by virtue of the fact that one of them has lied, the only guarantees you get are for the side of the Chimera chain of the base chains that haven't lied.
Good. 1 or 2 more.
Could you tell a bit about the difference between this and like the interchain security model of Cosmos?
So Cosmos uses a whole lot of IBC, and a bunch of the cross-chain atomic swap stuff is built on multi-phase commits. But a lot of the interchain security stuff is built on the concept that you can stake assets on other chains. And then if you can prove that the chain on which someone has staked, that they have misbehaved on the chain on which someone has staked, then they can be punished on some other chain, which can be useful if the chain in which they have staked, they made a mistake and it actually screwed up that chain. So punishing them on that chain is hard. In some sense, it's neither really here nor there. In fact, there you benefit from having those chains have completely different trust models so that you can definitely punish them in the event that they screw up a different chain. Whereas here, we're talking about being able to do atomic transactions when the chain trust models do overlap.
Yeah, so there is a difference in like here, there is a notion of overlap between the validators, but that's
Certainly is.
Okay, thank you again.